My name is Oleg and I'm from Moscow State University and the University of Washington. And today I'm going to talk about the physics of ultrasound generation and focusing in relation with high-intensity focal ultrasound therapy. And I would start with this image at the left, this image. And everyone, maybe many of us, tried to use magnifying glass to focus sunlight and on a small spot to start a fire. This is actually a quite effective way of focusing. And the same approach can be used for HIFU or high-intensity focal ultrasound therapy. But instead of using light, we can use ultrasound, which is here. And so in this approach, the energy propagates in the form of ultrasound waves, and then these waves are actually excited outside the body, and then they propagate inside the body through intervening tissue, like skin and other tissue, and focus in the small size region. And there, ultrasound can hit or make some mechanical action, and as a result, the tissue is destroyed. And this is actually the idea of using ultrasound for treating some diseases. And the idea, although is quite simple, like this magnifying glass idea, but of course behind that there should be understanding what kind of ultrasound should we use, how to generate this ultrasound, and how it propagates in tissue, and most importantly maybe how to focus it in that tiny tight region so that we can create the effect that we want. And let me start with the first description what the ultrasound is from the point of view of physics. Actually, for physicists, ultrasound is just one kind of type of waves. It's a wave process. And when you speak about the waves, the most maybe simple case, this is what is shown here. This is the waves that those are waves which are seen all the time when we are close to the ocean or sea shore, and they're beautiful. But looking at that waves, we do believe that waves can propagate long distance. They can carry energy, sometimes a lot of energy. That means that waves are a good way of actually transporting the energy without basically transporting the mass. So it's just pure energy shift. And it's not the only way the only example of waves that we know in nature. There are other waves. For instance, we use radio waves. And these waves are shown here. And radio waves are used, for instance, for radio, of course, for television, for our cell phones. All this is, all those are examples of electromagnetic waves which propagate, and then we use it. They're invisible. But also there are waves which are visible, which is light, this example. And light is also electromagnetic wave, just with higher frequency as compared to the radio waves. And the light, what we know, the light can be focused quite effectively. And light can be actually controlled quite effectively. And another example of waves which are used in actually now live is sound waves. I'm speaking now using sound waves, so all the information that you now hear, it's because of the sound waves which propagate from my mouth to the recording. In this case, you can hear it. And the sound is nothing but just compression and refraction or expansion of air or some medium. And for instance, when a tuning fork is vibrating with some specific frequency, then these vibrations, they actually result in compression or expansion of air, which is contacting the tuning fork. And then these phases of compression and expansion, they propagate. Not the air itself. The air, actually, it's, in average, it stays in the same place, but the compression and these phases, they propagate with the speed of sound, which is quite high, but not extremely high. So it's like several hundreds of meters a second or kilometers a second, depending on the medium. What is important is that if the vibration is periodic, then in space you have the same periodic structure. And the period in space is called wavelength. And the wavelength is a very important characteristic of any wave, not only sound wave, but any wave. The thing is that if you want to create a wave structure, the wave process, which can be focused or maybe controlled in the same way as we do with light, there is a very important condition which we should have. This is the condition is that the size of the source should be much larger than the wavelength. Otherwise, you cannot focus. And for instance, if we want to use ultrasound, in our case, for focusing inside tissue, then the wavelength should be millimeter size. Why? Because the sources are like centimeter or maybe several centimeters in diameter. So the much smaller means millimeters. And from that, we can easily calculate the frequency of oscillations. There is a simple relationship between wavelength and frequency. It's just speed of sound divided by frequency. And that means that if we want millimeter size, then for typical tissue, it appeared to be that the frequency should be of megahertz range. It means that when the source oscillates and emits this ultrasound, it should oscillate like a million times a second. 1 megahertz is million times a second. Quite high frequency. And so it's not like the same as tuning fork. It should be much, much faster. And how to do that? This is actually the big question.